Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to cover the discussions for week 2, hour 1 tutorial for both NFTF and also FTF. So since we have done the initial rate method in previous tutorial, which is week 1, hour 3, so we're going to do this real quick. So the learning objective is still the same as in the previous tutorial, where you need to find the order of reactions by using initial rate method. Given to you these reactions of nitric oxide with hydrogens to give you nitrogen gas and also water. So the following data was collected at this temperature. Note that each and every time you were asked to use initial rate method, only a number of experiments, like 3 to 4 experiments data were given. If you are given this number of experiment, then it means you don't need to do the graph. You can simply find the order of reactions by using initial rate method. Okay, so this time around, the questions didn't ask for order of reactions, but instead they ask you to find the rate law. So we know that the rate law is the combinations between rate constants and also order of reactions together with the concentrations of reactants. So by hook or by crook, you still need to find the order of reactions. And there you go, you can use the initial rate method. Alright, so the first thing you need to start with is by writing the rate law in general. So rate is equal to rate constant concentrations of nitrogen oxide to the power of m and concentrations of hydrogen gas to the power of n. In order for you to find the order of reactions, then we need to look at the constant value for both concentrations. As for nitrogen oxide, we have constant concentrations at experiment 2 and experiment 3, means we're gonna compare these two. And for hydrogen gas, we have constant concentrations at experiment 1 and also experiment 2. So we took the bigger value to be the denominator. So if we want to find the order of reactions for nitrogen oxide, then we need to keep the concentrations of H2 as constant. So we will compare between rate 2 over rate 1. So now, by keeping, we need to write this, by keeping concentrations of H2 constant, then we're gonna get rate 2 over rate 1 is equal to K NO with respect to the second experiment raised to the power of m, and also H2 power of n with respect to second experiment. So divided by, okay, this one we have experiment 1, so again power of m, and also hydrogen with respect to experiment 1. So we know that the H2 concentration is going to be kept constant, so we are going to cancel out these and also the K, leaving only the rate 2 over rate 1. So we know that our rate 2 over rate 1 will be 5 10 to the power of negative 5 and also 10 to the power of negative 5. So we have, we don't have enough space in here, so we need to do something. Oh, sorry. Oh my god. Okay. We need to create some space. Okay, now this number again. So we have, okay, so we have 5 10 power of negative 5 divided by 1.25 10 to the power of negative 5 is equal to, so your concentrations of NO for experiment 2 is 10 to the power of negative 3 divided by 5 to the power of negative 3, and don't forget the order of fractions here, which is m. Once we calculate this value, then we're going to get 4 is equal to 2 to the power of m. And we know that we can factorize this to become 2 to the power of 2 and also 2 to the power of m. Then we're going to have m is equal to 2. Alright, so we're going to get order of fractions for nitrogen oxide with respect to m. We're going to get second order reactions. So we have NO is second order. Okay. Coming up, the next part is finding the order of reactions for hydrogen gas. So we make a divider here. Right. So by keeping, so we says here that NO is kept constant. Again, we're gonna do some superpower here. We're gonna copy this. Okay. And paste it right away. Okay. Right. So change the comparison now between rate 3 and also rate 2. Okay, rate 3 and rate 2. 3 and 2. 3 and 2. Okay, so now we have 3 over 2. This is rate 3, this is rate 2. So substitute the value. Okay. So for rate 3, the value is 10 to the power of negative 5 divided by 5, 10 to the power of negative 5, and then as for this comparison, we're going to cancel out the concentrations of NO, leaving only concentrations of H2, where we have 4 10 to the power of negative 3 divided by 2 10 to the power of negative 3, not forgetting our order of reactions, which is N. Alright, so we're gonna get 2 is equal to 2 raised to the power of n, where here we got n is unique. So lastly, we got n is equal to 1. Therefore, we could conclude that concentration of H2 is first order. First order. Alright, so you only find the order of reactions, but the actual questions is to find the rate law. So knowing the order of reactions for both NO and also H2, then we're gonna combine it as a complete rate law. So lastly, you should write rate is equal to concentrations of NO to the power of 2, because it is in second order, followed by concentrations of H2 to the power of 1 because it is in first order. So the overall order of reactions is 3. Next questions, they ask you for the rate constant. So we know that rate constant is actually K. So how do we calculate K? We already know the order of reactions. Can we find the K? Yeah, you can simply take any number in this table. Maybe you take about this experiment 1. You can use this data, and also you can find the K. So now we know already the rate law. The rate law is rate K concentrations NO second order, H2 first order, and let's say we take the value at the first experiment. So we know the rate is 1.25. So if we rearrange this, we want to find K, then we're gonna get K is equal to, our rate is 1.25 10 to the power of -5 divided by, so our concentrations of NO is 5 10 to the power of -3. So 5 10 to the power of -3 but raised to the power of 2 times with our H2 gonna be 2 10 to the power of -3. Okay, lastly, our final answer would be 250. So what about the units? So let's check together. Since our rate is in molar per second, okay, so we have here molar per second, and for these concentrations to the power of 2 we have molar square. For this one we have molar. So now we can cancel out this molar with this molar. Lastly, you're gonna have unit of molar per -2, sorry, molar -2 per second. Alright, so this is gonna be your unit for our rate constant since it is third order. Okay, now proceed with face-to-face questions. So this is kind of new thing for you because it's your first ever time finding order of reactions by using graph method. So we have two types of graph, and it depends on the questions whether you need to do the linear or half-life graph. If the questions already tells you that they want half-life, then you can simply choose to do the half-life graph. But if the questions ask you for a linear graph, then you have to do the linear graph method. So it all depends on the question and the information given in the questions. Okay, so let's have a look at these questions. The data listed in table below were obtained from the radioactive decay of magnesium. So given to you time in hour and also concentrations of magnesium that being decayed is molar. So the questions ask you by graphical method. Since this question tells you graphical method, so you have two choices actually. You can choose whether you want to use linear or half-life. Okay, well, but don't rush. Read the questions carefully. Read until the end first. Okay, prove that these decompositions is a first order reactions. By right, you are free to choose whether you want to do linear or half-life. But I would suggest, if the questions already tells you to prove, it is easier for you to choose a linear graph because you already know that yes, this is a first order reactions, then I must do for the first order graph. Okay, Right, so for linear graph, it is actually a try and error method where if you are not given the order of reactions, then you need to try and error until you get a linear graph. It doesn't matter positive slope or negative slopes. But if the questions already tells you the order of reactions, then you only need to prove it, then choose for linear graph. As for this linear graph, you need to relate it to the integrated rate law equations, because the graph depends, the y-axis and x-axis depends on the integrated rate law. So we are going to have concentrations against time, but what kind of concentrations do we have? If we have zero order reactions, means we just have axis or y-axis of concentrations. If we have first order reactions, means our concentrations, we need to modify it into ln concentrations. And as for second order reactions, we know that our y-axis would be 1 over concentrations. So since you are given only concentrations, if you want to do the linear graph, then you need to make these concentrations become ln concentrations of magnesium. So actually for linear graph, you need to have an extra row for the informations, the new table instead. Okay, let's say I'll do the table here. Okay, so we take the time is in hour. Our time is in hour, and then our concentrations is ln concentrations of magnesium. Okay, so the first hour is 0 hour, so ln 1 is equal to 0, followed by 21 hour. Ln 0.5 is negative 0.69. You need to do this table in order for you to plot correctly. So we have negative 1.39, and then we have 63, then the value will be negative 2.08, followed by 84 hours. 84 hours will give you negative 2.76, and then we have 105 hours, negative 3.47. Then lastly we have hour of 1 to 6, then the ln concentrations will be negative 4.14. Okay, so once you've got this value, then you need to make y and x-axis has uniform scale. Okay, so let's check. So your hour should range from 0 to 1 to 6. So I have made uniform scales of 20 until 160. And then for ln mg, we have the lowest value of 4.14 and the highest value as 0. So we'll start with 0 and down here until negative 4.6. Okay, so now you have to plot all these points correctly in order for you to get marks. So for 0 and 0, we have a point here. Okay, followed by 21, negative 0.69. Negative 0.69 should be around here, and also 21. So the value would be around here. Okay. And then 42 with negative 1.39. 42 here, around here, with negative 1.39 around here. So maybe here. Followed by 63, negative 2.08, 63 around here, negative 2.08, maybe here. Okay, And then we have 84, negative 276, negative 276, and also 84. So 84, negative 276, maybe around here. 105 with negative 3.47, negative 3.47, and then 105, I guess here, somewhere around here. Not sure though if we can get a straight line. And then 126 with negative 414. 126, where's 126? So 126 around here. Okay, I guess, yep, a bit early point here. And negative 4.14. 4.14 must be somewhere in here. Okay, so now let's take a ruler to make a straight line. Okay, where's our 0? Where's the origin? So we're gonna have these and take the best fit. Best fit means you got most of them. Okay, right. Ooh, well done. We got nearly a perfect line. Okay, with a balance of points here. Okay, so we should try this color lah. Okay, yay, we got a straight line with most of the points. Okay, good. Alright, so this is our straight line graph. So is this the end of the world? Nope. Okay, prove that the compositions is a first order reactions. So since you already done the linear graph, so you can already say that this is a first order reactions graph. Okay, so you need to state that straight line prove that the reactions is first order reaction. So make some statement here, right? So straight line proved that this is a first order reactions. Okay, that's how you proved, since you already done the linear graph. Not you, it's me. First order reactions. Alright, so the rate constant is K. K in this case is the slope of the graph. So you need to find the gradient. Okay, so from here, we could take any point on this graph. So let's say I'll take the second point here and also the last point. Okay, we're gonna make a gradient. So you know how to make a gradient, right? Okay, 90 degree. Yeah. Okay, since you already have a point, so show on the graph, please show on the graph your gradient. It's moving. Oh, I'm having difficulties with this. Okay, I'm getting used to it. Alright, so for the next point here, okay, show on the graph your gradient, and you know how to find the gradient, right? So y2 minus y1 over x2 minus x1. So if we take this point of 21 and also 0.69. So this gonna be your y-axis, this gonna be your x-axis, and the other point would be the last point, which is 1 to 6 and negative 4.14. So to find your gradients, which is your rate constants, so we're going to relate it to the m. Okay, so our gradient would be, because this is a negative slope, so your m would be negative k, right? So we know that your m is equal to y2 minus y1, so we have negative 4.14 minus or plus 0.69, sorry, divided by, so we have 1 to 6 hour minus 21. So you get a value of negative 0.033. Okay, so since your gradient is negative, so m is equal to negative, so negative and negative, you're going to get positive. So lastly, your k is 0.033. So what about the unit? It would be per hour. Right, per hour. Okay, kenapa per hour? Per hour because ln concentrations we got no unit, and for time, oh sorry, this one should be hour. Mistake here, this one should be hour. Okay, alright, so we're done with this. Are we there yet? Oh, not yet. This means the half-life, if concentrations of A is equal to 1 molar. So since this is a first order reactions, okay, so first order reactions means our half-life would be ln 2 over K. So it doesn't depend on the concentrations. So you simply put the value of ln 2 divided by, so have you found your K? So here you have your K, 0.033. So simply put the value 0.033, then your final answer would be 21 hours. Yeah, so this is your half-life. For the last question, question number 3, it states the experimental data for the decompositions of N2O5 gas at 35 degrees Celsius are shown in table. So given to you information regarding time in second and also concentrations of N2O5 in molar. And then the questions ask you to plot a graph of concentrations of N2O5 against time. So it's already tell you what kind of graph that they want you to plot. Okay, so they want you to plot only concentrations against time, not ln concentrations against time, not 1 over concentrations against time. Meaning that this type of questions wants you to use half-life graph in order to determine the order of reactions. And then further being asked is the half-life of the reaction. So yeah, this convinces our justification just now. Okay, calculate the rate constant. So you need to find half-life, and then you need to find K, the rate constants. Okay, if you noticed, from the previous method, which is linear graph, you first find the rate constant, then only you can calculate the half-life. But as for half-life graph, you first find the half-life, then only you can calculate the rate constant. So they are basically gives both answers. But still you need to work on the instructions given. Okay, so as for concentrations against time, I've already make a scale for this value, since we have time range from 0 to 400 seconds. So here 0 to 400 seconds means that we start from origin here. Means we start from origin here. And then for our concentrations range from 0.02 to 0.2. So we have like 0.02 to 0.2. Okay, so now let's plot the point. Our first point is at 0 and 0.2. So here we have 0 and 0.2, means there's a point here. Okay, followed by 20 and 0.15. So where's our 20? Our 20 is around here. 0.15. So maybe 1.5 is here, maybe around here. Okay, and then for the third point, we have 50 second and 0.1 molar. So our 50 second and 0.1 molar is around here. And then followed by 160 second and 0.05. So 160 second and 0.05. 160 seconds should be around here. Okay, not the last one. 280 seconds, 0.03. 280 seconds, 0.03. And the last point would be 400 and 0.02. 400 and 0.02. Okay, so we have plotted all the points. Now, what we need to do is make a curve graph, okay? A quadratic graph for this. So make sure you have a very stable hand to connect all the dots. Since I'm doing it on screen, I hope I can get a beautiful graph at once. Okay, Bismillah. Yay! Right. So this is our graph of half-life. Then once you have plot the concentrations of N2O5 against time, next step you need to determine the first and second half-life. You cannot do only for first half-life, because from the first half-life you cannot determine what kind of reactions is this. So we need to do it 2 times. So half-life means you reduce the concentrations to half of its initial concentrations. So if we reduce the concentrations from 0.20 to become 0.10, then you're gonna have a point at here. So we're gonna look at the time taken here. So we take a ruler to make it more precise. Okay, we'll see that the half-life is 50 seconds. So we need to label it. So this is gonna be 1/2 initial concentrations. Okay, and then this is gonna be your first half-life, so we need to label it. This is gonna be your first half-life. Okay, as for second half-life, you need to reduce another half of the concentrations from the first half-life. So from 0.10, if we further reduce it, we're gonna get 0.05. So at 0.05, we need to take it all the way to the curve, and then we're gonna get the time for the second half-life. So this will be around 160. Okay. This is 50. Let's say this one is the point here is 50, and then the point here is 160. But our second half-life is not necessarily 160. It's actually being measured from here to here. Means it will be around 100, 110. Okay, sorry, this is the second half-life. So by right, if you compare this value 50 and also 110, we could see that our second half-life is double from the first half-life. So we could write that our second half-life is equivalent to 2 times of our first half-life. Therefore, the order for these reactions is second order. How do we know this? By looking at the difference between first half-life and also second half-life. So we could see the half-life doubled from the first half-life. Okay, right. So next questions is to determine the half-life of the reaction. So we know already the half-life gonna be 50 seconds. So therefore, your half-life is 50 seconds. Okay, so you've already answered the questions regarding half-life. 50 seconds, or maybe, yeah, seconds. And then calculate the rate constants of the reaction. Since this is second order reactions, in order for you to calculate the rate constant, then you simply use the formula half-life is equal to 1 over K initial concentrations of N2O5. So we know that our initial concentrations for this species is 0.20. So simply substitute the value. Then by rearranging this formula, then we're going to have K is equal to 1 over. So our half-life is 50 seconds. And then the concentrations is 0.20. Right? So once we calculated it, we're going to get a rate constant of 0.1. Okay, so what about the unit? So look at our y-axis. So we have second and also molar, and then once we take it to the upper part, then it would be per molar per second. So from the unit itself, we could say that this is really a second order reactions. Okay, so yep, we're done with the tutorial for week 2 hour 1. So if you've got anything to ask, you can simply text me, or you can make an open discussions on Google Classroom. Alright, okay, so thank you everyone. Assalamualaikum.